All right, welcome back to class. So we're back after our 3-day weekend. Um, the plan today is to start section 6.3 and 6.4 on volumes by the shell method and work. And then we'll have a supplemental video posted on 6.3 and 6.4. I'll try to get that out tomorrow. We'll see how time progresses. It might be not until Friday that I get that out. So just a reminder that this is a hybrid course. So kind of for the first week, the additional like 60 or so minutes of instruction was really just getting all of the tech up and running, getting acclimated to all of the tech, reading through the course materials, the syllabus, all that kind of stuff. And so the supplement for this week, look for that available on Friday, well, tomorrow or Friday. I've also posted my office hours. So I have some office hours each day in the morning, and the link is posted on Blackboard. Note that it's different from our class meeting link. All of my classes have a different class meeting link, but my office hours are for everybody. So there's a separate link for that as well. So look in the Blackboard folder, the Zoom folder under the link for Zoom links, and in there you'll see that I've added the office hour days and times as well as a link for office hours. So make sure to use the right link if you're looking to join office hours. All right. And then we have two quotes of the day today since I kind of group my classes as Monday, Tuesday, and then Wednesday, Thursday. And if I, since we missed Monday, we're kind of doing a second quote today to make up for it so that I'm not always trying to remember, wait, does Tuesday go with Monday or does Tuesday go with Wednesday? So the two quotes of the day today from the Roman lyric poet Horace: "There is a mean in all things, too far to the right or left of which good cannot be found." Um, so obviously a translation from Latin, um, but I think it's good advice in general. Try to stay away from the extremes, stay a little more towards the middle, and things tend to work out a little better. And the second quote of the day, I actually have a little bit more to say because we have such limited time in this class with the hybrid component. I'm going to cut this a little short, but um, kind of the idea here is to make strategic use of the learning curve. And I might have to reacclimate myself to drawing because with the split screens, my trackpad works a little bit differently. But so this will give me a chance to get used to the different proportions as well. So making a strategic use of the learning curve, there's a couple of different ways you can think about the learning curve, and this is maybe um, one of many ways to think about it. But if you put in a certain amount of time or effort versus um, how good you are at that thing, how um, efficacy. Oh geez, my writing is pretty terrible with this setup. Um, you can actually achieve a pretty decent amount of knowledge or uh, whatever it may be, fluency in a sense in a field um, by putting in a moderate amount of time or effort. Now, like, putting in an hour watching a YouTube video is not going to do it. But what I mean is that, there's that saying that like to become an expert in a field, you need to put in 10,000 hours of effort or like basically a full-time job for 5 years or a part-time job, like 20 hours a week for 10 years or something. Um, you know, that's an enormous amount of effort. But that's to get kind of all the way out here on the curve. But if you put in, a couple hundred hours of effort, if you know, take a course in a topic or make, a pretty dedicated study of a topic, maybe over a couple years, you spend, an hour and a half studying that material a couple times a week for 2 years, you can actually be, pretty competent in that topic. You're not going to be nearly as good as the experts, but the experts have to put in so much more time to gain that expertise. And what this allows you to do by having a lot of topics like this that you're kind of, in a sense, a jack of many trades, well, that allows you to have a wider breadth. And, a lot of what school focuses on is depth. So you focus on becoming an expert in one particular narrow area, but you also want to have some breadth as well. That allows you to pivot a little better. And it just allows you to communicate better with different people in different fields, to kind of know the lingo, to understand what their perspectives are, what things they care about or don't care about. Um, so I think there's benefit to that. Kind of, you don't want to be a jack of all trades and master of none. But on the other hand, you don't want to be so hyper specialized that you're a master of one very specific thing and don't know anything about anything else. So I think balancing the two is really beneficial. And when I'm deciding what I want to learn, uh, what is everything I do now, Office wants to pop something up and tell me that has some new feature, and I have to constantly click, got it. I feel like I do that at least 5 times a day now. So sorry about that. There we go. Now I can draw an arrow. Um, so this this idea I think is related to, you know, what knowledge do you want to pursue? And when I think of, what things do I want to learn or what things do I want to focus on, I kind of split it into 4 quadrants. One division has to do with time constant. So if I learn something, how long does it take before that knowledge is essentially useless? So is it very dynamic or static? Does the value of that knowledge decay to zero quickly or slowly? And the other criterion I look at is it trivial or foundational? In other words, I learned this one piece of knowledge. Can I connect it to a lot of other pieces of knowledge that I have? Or can I build on it to learn more advanced things? That would be more foundational. Or trivial is just kind of an isolated island of knowledge that I have, and I can't really build on it very much. I can't really connect it to too much else. Um, Now, my personal favorite is static foundational. That's very mathematical, right? Like you learn some math theorem, it is going to be the same theorem in 100 years. And so that, the value of it never really decays. And you can use that theorem as a building point for more complicated stuff. But that being said, it's not bad to be in any of the other quadrants, just realize the trade-offs. So a lot of people like being in the dynamic trivial space, people who are in, say, tech support, right? Things are changing all the time. They just enjoy kind of keeping up with all the changes, and they enjoy being the go-to person who has kept up with all those changes. They can be a resource to the people who, don't like that or don't have the time to do that. So there's value in each quadrant, but, I tend to lean towards the static foundational side of things, right? I'd rather learn something interesting about the politics of ancient Rome than, the politics of whatever happened, in the last month or something like that. Um, or, the classic example I use is you watch a football game this past weekend and you say, oh, there was this cool play that happened. You can talk about it with your buddies at the water cooler, Monday, Tuesday, Wednesday. If you bring it up a month later, they're going to look at you kind of strange, right? So, um, I'm not saying that you should pick one quadrant or not the other quadrant, but be aware of the trade-offs. And at least this is a model that I think about. And it also warrants saying that, you know, my idea here is if I'm trying to learn something to say better my career or make myself more effective at what I do. That's a wholly different thing from, you know, looking for something enjoyable, right? If I'm just doing something to relax or chill out or, in my leisure time, to kind of shut my brain off, that's a different story. So I'm not saying don't watch football if you like watching football and like hanging out with the guys, but, if you're watching football to try to connect with people at your job, maybe there's something you can do, that would be a little less, uh, that would require less upkeep, so to speak. Personally, I just don't like learning something and then having to relearn it. I'm kind of like a get off my lawn kind of person. I'm like, every time Word updates or something and there's some new feature, I'm like, why did they do that? I want it to work the same way it did, 12 years ago. Um, so anyway, all right. So the work for today focuses on, again, volumes by the shell method and work. We're going to introduce both topics and then keep an eye out for the supplemental video, which will have a couple additional problems on each of those two topics. Okay, so let's look at finding volumes using the shell method. We'll take a motivating example to start with. Consider the solid obtained by rotating this region about the y-axis. What is the region? It is the region bounded by y equals sine x squared from x equals 0 to x equals root pi. And it looks something like that. It's maybe a little steep on the right side there, but it's good enough to get us the basic idea. Okay, so there's my region. And again, we're rotating about the y-axis. So what does my figure look like, my solid? I have a mirror image on the other side when I rotate around. I missed my mark there a little bit, but close enough. And my solid rotates around like this on the top and on the bottom as well. So there is my solid. And just for reference, I'm going to draw maybe this interior kind of dip. I'll draw as green. These colors don't reference the original region R, but just so we can distinguish them a little better later, and red on the outside. So I have kind of what looks like maybe a bundt cake pan turned upside down, if you've ever seen a bundt cake pan, where like the outer edge is red and the inner is green. Let me actually make a copy of this because I don't want to have to draw it again. Make a copy of this and bring it down here a little bit. All right. Okay, so last time we discussed finding volumes using the disc or washer or wafer method with the perpendicular cross section. Let's take a look at that here. So let's say I take a cross section. My my symmetry is about the y-axis, so it makes sense to take a cross section perpendicular to y. Here's the y-axis. There's my plane perpendicular to y. And I see if I pull this out, my outer rim of this kind of bundt cake pan, so to speak, the red bit is going to give me a circular cross section. And the green bit is going to give me an inner circular cross section. And the solid is going to be between those. So I have an area in here that's the area between the red and the green circles. I see my green circle is going to have a radius, as is my red circle. These are circles because I rotated around, so same distance all the way around. So my area is going to look like pi times, well, this green intercept here is going to be at a radius of position, let's say x1. Oh, wrong order. And the red, let's say at x2. Okay. But remember, if I'm taking my cross sections like this, I want to stack them up along the y-axis. So I really want area as a function of y. And then I'll let y go from like y equals 0 up to maybe y equals 1, right? But I have a little problem. I need to solve for my xi squared in terms of y. That's not going to be very nice, right? I'm going to have this kind of like arc sine stuff and have to integrate this arc sine. Maybe I could find a way to do it. I don't know. Maybe if, after we're done talking about all of our integration techniques, which we'll be talking about in chapter 7, maybe we can make it work out. But at the very least, it's not going to be a very nice integral. Um, and I think it's going to be quite a bit of a hassle. I also kind of noticed that I have like, even if I did go the arcsine route, I kind of have like a non-one-to-one function I'm trying to invert. So I have like an inner inverse and an outer inverse, right? So this height can be gotten, this output can be gotten with two different inputs. So I have to be careful about that as well, right? This is just going to not be an easy problem to do. So what could I do instead? Well, maybe what I could do is I could say I really just want to deal with things vertically, right? I mean, I would like to integrate something like sine x squared and not something like arc sine. Is there a different approach I could take? And the answer is yes. So we have kind of a fundamentally different approach that we could take. Instead of taking little slices and kind of stacking them up to create our solid, we can take little cylinders or little, I suppose, technically cylindrical shells. So I could take what's almost like a cylindrical cross section. How I think about this, I don't know if this is, something any of you have ever done, but if you've ever gone to any of those like, um, oh, what are they called? They're like, kind of Renfest, Renaissance Fair kind of things, but like for like revolutionary times, you like go out to Frick Park or something and they have somebody who's like doing, the shuttle and the loom thing, like making fabric, or they're all dressed in like, 1700s clothes, and there's people shooting muskets and stuff like that. Um, and I always remember when one of these that my sister and I went to, they had this little setup or whatever, where what you did is you started with a string, they just gave you a piece of string, and they had molten paraffin wax there. I don't think paraffin wax gets all that hot, so I don't think it was that dangerous. Um, it sounds a lot more dangerous than it was. But you take your string and you dip it into the wax and you pull it out, and there's a line of kids. So then you go to the back of the line, and when you come up again, you dip it again, and that first layer of wax around the string is cooled, and then you get another layer of wax built around the first layer of wax, and you go back to the back of the line, come back up. By then the wax is cooled again, you dip it again, you get another layer of wax around, and you do this as many times as a young kid can tolerate doing it, and it builds up and makes a candle. So you have this piece of string covered in lots of cylindrical shells of layers of wax. And in some places they'll actually do it with your hand. You like put your hand in cold water, and then you immediately put it in the wax, and then you have a little wax thing on your hand, and you hold your hand really still and you wait a little bit and dip it back in the wax, and then it makes another layer and so on, and you can like cut it off and it makes a little mold of your hand. So that's what I kind of think here. We're almost like starting at the innermost point and building a little shell, and then a shell around that, and a shell around that. We're varying the heights of the shells, and that's building out this solid from the inside out, from the kind of center of the axis of rotation out to the outermost point. So this shell is taking the place of the perpendicular cross section. So if I pull this shell out, I'm going to try to draw it pretty, or somewhat nicely, let's say. I won't say pretty nicely. I'm not that good of an artist, but all right. So there is our little cylindrical shell. Now this shell is going to have radius x. It's going to have height. If this is my function f of x, it's going to have height f of x. And it's going to have like thickness or kind of width, delta x. Now you might say, well, wait, isn't the radius a little smaller on the inside than on the outside? Or isn't the height at the inside a little different than the outside? Yeah, when we have delta x, that's true, but eventually we're going to be taking a limit as delta x goes to 0. So we'll have more and more of these shells that are of lower and lower thickness. And so then the difference between the inner and outer radii, or the difference between the heights at the inside or outside or somewhere in between, will be negligible. Now, if I imagine cutting this down one side and kind of rolling it out, what I'll end up with is essentially a little kind of like cuboid type thing. This will have thickness delta x. It'll have one dimension, f of x, and the other dimension will be the circumference. Like if I had a little soldier standing on top of this wall and walked all the way around it, how far would they walk? Well, that circumference, I think, is just going to be something like 2 pi times the radius, or 2 pi x. So one of these cylindrical shells has volume 2 pi x times f of x times delta x. And I have a bunch of these. I have an inner one and then a next one all the way out. So I'm adding up a bunch of these. And then I take delta x going to 0, number of shells goes to infinity, and I end up with an integral of 2 pi x f of x dx. I have to be careful here. When I'm doing the cross-sectional area, I just start adding cross sections at one point and go all the way to the other end of the figure. I don't start adding shells at minus root pi and stop adding them at positive root pi. I start adding shells at the middle here. I start adding shells at the axis of symmetry and go out from there. I'm actually going to integrate, in this case, from 0 to root pi, or from kind of my axis of symmetry out to the edge. So I do have to be just especially careful about my bounds on these. So when I say I integrate from A to B, that's not A to B where that covers the kind of entire, in this case, a chunk of the x-axis that I'm moving along. It really is like, this is A, kind of, and this is B, kind of. In this case, this is A to B. But I could also imagine that if that in another situation, I could have a region over here rotating about this axis, then this would be A and this would be B. So it's not always the axis of symmetry, but we really have to get a handle on what does the geometry actually look like? Where should my bounds be? What should they be? What makes sense here? So we really have to understand this, what the geometry looks like, both in the 2D and 3D, to, I think, have a good handle on how we should set up these bounds. I don't think there's a really easy kind of generic way to say this is how your bounds should be set up. But it's going to be kind of the innermost piece of the region that's closest to the axis of symmetry out to the outermost region, or outermost part of the region. So what would my volume here be? 0 to root pi of 2 pi x. That 2 pi x is just always there. That's from that circumference. And then f of x is sine x squared. Right? F of x came from this height that started at 0 and went up to sine of x squared. And this actually is an integral we can do by u substitution. I think I'm actually going to go down to go back to just a single screen because my writing is getting worse and worse. But just use the u substitution here and you can work out the details. So maybe as an exercise, as practice, do this problem. All right, give me 1 second here. I'm gonna redo my windows. Thought I was being slick with my 2 monitor setup, but it's not going as smoothly as I had hoped. I just recombobulate my windows here and then we'll jump right back into it. Okay, sorry about that. Thought I could work out having notes on one screen and writing on the other screen, but I think that'll require a little more practice. Okay, so that is the idea of cylindrical shells using the shell method. We build these shells and work inside out. Now, in theory, we could evaluate the volume using either method. But again, in practice, sometimes it's going to be a huge hassle doing it one way, and this integral is much easier to do. So I'd rather use shells for this problem. There will be other problems where shells would be a huge hassle. Maybe this factor of x really messes things up, but maybe the square nature that tends to come out of this of the cross-sectional method, maybe that works better in other cases. So we're just adding a tool to the toolbox, basically. All right. So let's look at another example. Compute the volume of a solid obtained by rotating r about the y-axis, where r is this region. So let's get an idea what this region looks like. 1 sec. Sorry, I had to sneeze there. I hope I muted myself in time to not blow your ears out. Um, all right, so my first function is 4x minus x squared, or that is x times 4 minus x. I know this is a quadratic opening down and has roots at 0 and 4. And my other function, y equals x, just this 45-degree line. And my region of interest, we see we only have one finite region here, that little bit there. We are rotating about the y-axis. Let me actually erase that 4. I don't want that 4 to get confused later on. So this green 45-degree line going up to the right is going to mirror around to the left side. I'll draw it a little bigger on both sides. And then I have this blue arch on the right side and on the left side. That's rotating around, making this kind of like cone-shaped thing. It's a little bit like an ice cream cone on the outside, but with like some puffiness on the inside or something. So this is my volume. I have to be a little bit careful here because if I look at a shell, it's actually not going all the way to the bottom. A shell is going to look like this. It's going to have its top being the blue function and its bottom being the green function. So what's my shell going to look like? I'm going to draw it less accurately this time. It's going to have a height that is blue minus green. It's still going to have a radius. My my axis of rotation is 0 here, so its radius is still going to be x. And its thickness is still delta x. So those bits stay the same, but my height, blue minus green, isn't just going to be like f of x, 4x minus x squared. It's going to be 4x minus x squared blue minus x minus green. I do need to figure out my bounds of integration. I know that I'm going to start adding shells at 0 at the innermost point near the axis of symmetry, and then I'm going to work my way out. But be a little careful. I'm not going all the way out to 4. That was just where blue intersected the x-axis again. Actually going out to here. So where does 4x minus x squared equal x? Or where does, what would this be? If I add x squared over to the other side, I get x squared. Subtract 4x minus 3x equals 0. This is either x equals 0 or x equals 3. So the outermost bit of this solid, which stops whenever those two curves intersect, is at x equals 3. So I start adding shells at x equals 0 and keep putting more and more shells around until I get to the outermost shell at x equals 3. I don't add shells from -3 to 3. Then I would be kind of like making the solid twice. I'd be going from the outer shell all the way to the inner shell, and then going from the inner shell all the way to the outer shell again. So I don't start over here. I just go from 0 to 3. Because when I add a shell that's kind of off to the right that wraps around and covers the volume on the left as well, right? Okay, so my volume is going to be the integral. I'm integrating from 0 to 3. 2 pi x from my circumference. The f of x, the height, in this case is going to be 4x minus x squared minus x, the difference between those top and bottom functions, or that's going to be 3x minus x squared. And then that delta x just in the integral turns into a dx. That's kind of the thickness of my shell, which becomes infinitesimal. And of course, from here, I think we can pretty comfortably do this integral, right? Just a polynomial. So just because we're a bit tight on time, I'm going to skip over doing this integral and the last one and leave those as exercises. So check yourself, go through, do the integrals on your own, check on Wolfram Alpha or something, make sure you got the right answer. Any questions on cylindrical shells? So really the challenge here, the new idea is just carefully setting up the geometry, drawing reasonably accurate pictures so that you know what's what, understanding how the shells work, and pretty importantly here, maybe the biggest practical difference from the last section is that the bounds are a little wonky. We just have to, when you think about it, it makes sense, but if you were going quickly and not being careful, you could easily double your volume by going from one extreme to the other and kind of building shells from the outside all the way in and then back out, essentially building your solid twice. Any questions? Okay, so moving on to section 6.4 on work. This is where I pretend that I know more physics than I do. So the bane of mathematicians' existence is units. And so usually we just, ignore units completely. But I suppose in work, we actually have to discuss units. So let's take a look at some of the physics background and then try to knock out maybe a simple example. And then we'll leave a couple more examples for the supplement. Okay, so a little bit of physics background. Newton's second law, F equals ma, or that's m times the second derivative of position, right? Acceleration being the derivative of velocity, which is the derivative of position. So F stands for force, m mass, a acceleration, and s is position. Sorry, P stands for momentum, and I guess because m stands for mass. So mass took momentum's name, so momentum bullied position and took P, so S gets to be position. I'm not sure why S, but it is what it is. The standard international units for these quantities, the units of force are newtons, abbreviated N, mass kilograms, acceleration is in meters per second squared, and 1 Newton is 1 kilogram meters per second squared. I think maybe newtons isn't technically an SI unit. I forget how that works. Maybe these are all the SI units, but close enough. What does this mean? This means that a force of 1 Newton applied to a mass of 1 kilogram yields an acceleration of 1 meters per second squared, or it yields a change in speed of the speed changes 1 meter per second each second. I don't know if it's imperial unit or US units or whatever, but like our US units of force are pounds, of course. Note that force is pounds or newtons. So pounds associate in some sense directly with newtons. Pounds don't associate directly with kilograms, even though we typically say, oh, well, 1 pound is about 2.2 kilograms. There's kind of the implication there that we're working at kind of, some standard gravitational frame on Earth, like, about the surface of the Earth. So pounds really associates directly with newtons. Uh, they're both measures of force. So what is work? Oh, oh, cool. Dennis put in the chat, momentum is represented by P because it originates from Latin word pellere, which means to push or to drive. Position is S because it comes from spatium, which means space. Cool. I didn't know that. Thank you for thank you for letting me know that. Uh, maybe I should maybe I should be more interested in units and things from physics, but yeah, that's pretty cool. Um, okay, so yeah, so work is force times distance. So if I'm applying a constant force, I have some block of mass that's kind of sitting on the ground. I have to push against it to get it moving. Let's say it's on a pretty slick ground, like ice or something. I have to push against it to get it moving. If I push applying a force and I apply that much force over a certain distance, I've done a certain amount of work. I've kind of roughly speaking, expended a certain total amount of energy to apply that force over that distance. That's kind of my energy expenditure, roughly speaking. That's the amount of work that I've done. So work equals force times distance. I multiply the constant amount of force that I'm applying, maybe 5 newtons, over the distance that I'm applying, and maybe 10 meters. Well, if I apply, say, 5 newtons over 10 meters, and I'm saying work is the product of the two, I have 50 newton meters. Or a newton meter is a joule, Joule. So the units of work are newton meters, newtons times meters, or joules. 1 newton meter is the same as 1 joule. Or in the US system, the unit of work is foot pounds. Sometimes they call it foot pounds and sometimes they call it pounds feet. And I think there's like a subtle linguistic difference there that, like, if you call it pounds feet, that kind of tends to go with this way, and foot pounds tends to kind of associate with that thing. But I'm not exactly sure, but we're just going to call it foot pounds. I think maybe foot pounds is more like with torque or something, but we're just going to say foot pounds. So if that's, grating to your ears, if you know more physics than I do, then I apologize. But 1 foot pound is approximately 1.36 joules. So, you know, 1 foot pound is kind of on the order of magnitude of 1 joule or 1 newton meter. They're not exactly the same, but they're not off by a factor of 100 or something like that. Okay, so a couple basic examples. We haven't gotten any calculus yet, just kind of laying the foundation. So how much, let me pop this down to the next line so it looks a little nicer. How much work is done in lifting a 100 kilogram mass 10 meters off the ground under standard gravitational conditions on Earth, where acceleration due to gravity is 9.8 meters per second squared. Okay, so what do we have here? We have that work is force times distance. And we have that force equals mass times acceleration. Well, our mass is 100 kilograms. And our acceleration due to gravity, g, is 9.8 meters per second squared. So our force is 980. Kilograms meters per second squared. Or what was that big jumble of units? Well, that was what we call a newton. So that is 980 newtons, our kind of standard unit of force. So the force being applied by this 100 kilogram mass, or kind of like roughly speaking, like if I if you put this in my hands, this 100 kilogram mass, and I had to just like hold it, like how hard would I have to pull on it? I'd have to pull with 980 newtons if I'm standing about on the surface of the earth to keep the thing from falling onto the floor. So that's the force that's being exerted by this mass downwards towards the floor. So to move it upwards or downwards, whatever, I have to apply that 980 newtons of force. I have to apply that force. And to move it 10 meters, uh, I have to apply that constant force. Where 10 meters isn't far off the surface of the earth, so the force isn't going to change very much at all from this 9.8. I have to apply that constant force over 10 meters. Now, if I was raising this up to the space station, I mean, I don't, then things might get, it might get a little lighter the further away I get from Earth, right? Might have to take that into account. Or certainly if I'm taking it up to the moon at some point, it is, essentially weightless. But we're staying close to the Earth, so the gravitational acceleration is treated as constant. So I have 980 newtons of force that I need to apply over 10 meters, or this is 9,800 Newton meters, or 9,800 joules. This is the work done. So if you have a 100 kilogram mass, or what we would call maybe say roughly 220 pounds, if you wanted to lift that to the top of a 10-meter building, a 30-foot, say roughly building, it would take 9,800 joules of work, of something like energy, to to pull that up to the top. Okay, how much work is done in lifting a 20-pound weight 8 feet off the ground? Kind of nicely enough, this is probably the only time in all of science that this happens. This is an easier problem than using the SI units. Why is that? Well, work is force times distance, but 20 pounds, the way that we kind of measure like weight, so to speak, in the US, is actually a weight, right? The way that a lot of folks measure weight, or kind of like how hard something is to lift up. Most people use kilograms around the world, but we use pounds, which nicely enough is essentially just a force. So when we say pounds, we're talking about pounds force. Sometimes it's written LBF. I think there's a slightly different pounds that is like pounds of mass or something, but when we just say pounds, or you step on a scale and it says this is how much you weigh in pounds, that's the pounds we're talking about here. And this is just the force. So we have 20 pounds. So if I was, if you handed me this weight of 20 pounds, how hard would I have to pull up on it to keep it from crashing to the floor? I'd have to exert a force of 20 pounds to keep it still, or to, move it up or down a little bit, whatever. If I move it 8 feet off the ground, I have to exert a force of 20 pounds over a distance of 8 feet. So 20 times 8 is 160 foot-pounds. That's the amount of work that I would need to do. Or about 1 1/3 of that in joules. So, somewhere in the ballpark of a little over 200 joules of work done. That's kind of the energy expenditure it would take me to lift this 20-pound weight 8 feet in the air. Okay, so if I have a constant force over a distance, I can figure out the work, kind of the energy expenditure, how much effort it's going to take me to get this job done, by doing work equals force times distance. Now, we haven't touched calculus yet. You might think like, did I just go crazy and start teaching physics for some reason? Well, here's where calculus comes in. We have this foundation. We know how to handle constant forces over a distance. What if I have a continuously varying force? What if I'm pushing this block along the ice, but sometimes I push really hard and sometimes not so hard? And well, now I can't just do force times distance because the force that I'm applying to the block changes over time or over space. So if force is a function of x, I apply different forces. I push harder at some spatial points and less hard at other points in space. And I do that over a distance for this varying force. What was my total amount of work done? What was the total energy expenditure if my force varies? And, spoiler alert, it is the integral of force over the distance. How do we get here? Well, one really nice thing about this strategy is this is actually something that we've seen before. We saw the idea of Riemannian integration, right? Was I take my nice continuous curve, I say, well, finding areas under these messy, like smooth curves is kind of annoying. I can find areas of boxes really easily. I can split my curvy area into a bunch of boxes, find the areas of the boxes, add up those areas, and then let the delta x go to 0. That recovers the smoothness of the curve and lets me work with boxes. Well, what is a box? It's just saying over this little chunk of distance, this little chunk of x-axis, pretend that I have a constant height, right? Or going back a couple sections, where was I? Here. I can take my little cross-sectional slice and say from here to here plus delta x, just use this same washer and then change the size of the washer and use that for the next delta x. I can compute areas of washers, okay. I can compute area and then multiply it by delta x to get the volume of the washer. I can compute the areas of a bunch of different washers, let delta x go to 0. I have more washers that are thinner and thinner. I recover the smoothness of the solid and I can get my area. Or I have my cylindrical shell. I have a cylinder of thickness delta x, wrap another one around it, wrap another one around it. I can compute those volumes pretty well. I need to, fudge a couple more things because this, the inner and outer radii and stuff is a little different. But when I let delta x go to 0, the thickness go to 0, use more and more shells, I recover the smoothness of the solid, and I can compute the volume that way. So this idea of split the problem into tiny chunks, a whole bunch of tiny chunks, on each chunk approximate by essentially a constant, add up all of those approximations, and then take a limit as basically chunk size goes to 0 and I get more and more chunks. That idea works here as well. I have a spatial distance x going from A to B. I'm moving this object from position A to position B while applying a force that is dependent on the position. I split the interval into n subintervals, A to A plus delta x, A plus delta x, A plus 2 delta x, and so on, split into a bunch of intervals of width delta x. On each of those intervals, I just treat the force like it's constant, like it's, say f at the beginning of that interval. Then the work done, if I use I subintervals, can be approximated by the work done on the ith subinterval can be approximated by the say the force evaluated at the beginning of that interval. I just say, okay, when you were at this position, how much force were you applying over the next millimeter? Let's just pretend that you're applying that exact same force, that constant force. The work on that interval is force times distance because we're just taking constant force over that small interval. And the total work is approximately the sum of those force times distances, or the sum of f of xi times delta x, the little increments of distance. We take n to infinity, delta x to 0, just like we've seen before, and we end up with the work is, is the integral from where I started pushing to where I stopped pushing from A to B, that spatial distance of f of x, this continuous force curve, dx. So work is the integral of force. Something really interesting. Imagine I have my block. I might push it for a while and then like pull it for a while. Or I might, Walter Lewin, the physics professor, gives the example of you have a briefcase on the floor next to your desk and you pick it up, put it on the desk, put it down, pick it up, put it back on the desk, put it back on the floor. So I applied a positive amount of force to pick the thing up, but when I put it down, I actually apply a negative amount of force. In other words, I could imagine if I had like a string attached to it and it was attached to an alternator, I could push it off the desk and it falls down to the floor, and I could use that to say charge up a battery, right? I could extract some energy out of that. So I pick it up, put it down, pick it up. I do that 1,000 times. If at the end I put it back where it started, I've actually done zero work because I applied some positive force that I've added up and then negative the same amount of force and positive and negative. You can get very tired while doing no work, as he says, right? Or if you go and you're sitting on your couch and you say, all right, I got to do something, and you go up and you run around the block 10 times and you come back and sit down on your couch, you've done no work. No, I mean there's things like air resistance and stuff, but ignoring those things as we tend to do to make our lives simpler. So work isn't necessarily how tired you get. You might have to expend a lot of energy because maybe your system for doing these movements is inefficient, but you can imagine like a car with regenerative braking can go up and down a mountain, you know, a lot more times on a tank of gas than, one without regenerative braking, because it's taking advantage of the fact that when it's coming down the mountain, it actually gets to recover a little bit of that energy. And in a perfect world, it could go up and down a mountain a whole bunch of times. And, you know, if it could recover all of the energy that it spent getting to the top every time, then then it would only be paying something like the air resistance costs, or costs of things like air resistance, rolling resistance, friction, heat, so on. Okay. All right, so since we're about out of time, we will leave these till next time, but we'll do an example of Hooke's law with a spring. We'll do an example of pulling a rope or a chain on the top of a building. We'll do actually a couple related examples to this as well in the supplement. So we'll do a problem or two on cylindrical shells in the supplement, and then a few problems on work. I might kick a little bit of work. I might kick one last problem to next week, depending on how long the supplement is getting. All right, let me stop the recording.